Watch what happens. So cool. I could watch this all day long. This is so cool. Hello, welcome to this learning module. It's going to explain everything about organic chemistry, all 2 semesters. It's amazing. You're going to wonder why we never told you about this earlier. Main takeaways that I want you to take away from this video. Some of them you already know. Negatives attack positives. You probably already know this. Second takeaway, the only way to form a bond is to pump electrons into an empty orbital. That may not mean much to you now, but it will by the end of this video. The only way to form a bond is to pump electrons into an empty orbital. And finally, orbitals exist. Then we put electrons into them. Sometimes students get the causality backwards, that we have these electrons, we need to invent some orbitals for them to live in. That's not true. It's the other way around. Orbitals exist. Then we can put electrons into them. Those are the 3 takeaways. Keep these 3 points in the back of your mind as we go through the rest of this video. Orbitals exist, then they are filled with electrons. Let's start with the hydrogen atom. You may remember the hydrogen atom. Yes, hydrogen atom with its 1 electron in the 1s orbital. You've heard of the hydrogen atom? Good. Okay, the question for you is, does a hydrogen atom have a 2p orbital? What do you think? Does a hydrogen atom have a 2p orbital? Have you ever thought about it that way? Take a second, take a guess, make a hypothesis. Does a hydrogen atom have a 2p orbital? The answer is yes, it does have a 2p orbital. It must have a 2p orbital. How can I prove that to you? You may recall from previous courses the atomic emission spectrum of hydrogen, the Balmer series. The atomic emission spectrum of hydrogen, if you had that explained to you, you may have seen it in a visual like this. This is a grossly inaccurate visual, but it does its purpose for what we're talking about here, that the 1s electron in hydrogen you can excite up to higher energy levels. You can excite it with light or heat or electrical currents. And when that electron relaxes back down to lower energy levels, it must give off a quantum of energy, and we call that energy a photon. And if that photon of energy has the correct energy of visible light, then we see that photon as a visible photon. And that's where we get the Balmer series, when electrons at higher energy levels relax back down to the 2nd energy level, that those energy levels happen to be correlated to visible photons of light. What are these higher energy levels? They're other orbitals. The 2s, the 3s, the 2p orbital, the 5f orbital, these are the other orbitals. The hydrogen atom has all the orbitals. Orbitals exist. Then we put electrons into them. All these orbitals are higher in energy and less stable, so if the electron finds itself in the 2p orbital, it will relax back down to lower energy levels, give off a photon. Sometimes we can see that photon, but yes, hydrogen atom has a 2p orbital. Orbitals exist, then we put electrons into them. Okay, so what about bonding? You may remember the hydrogen atom, diatomic hydrogen, the hydrogen molecule. Hydrogen, H2 gas, is formed when 2 atomic hydrogen atoms with their 2 electrons in their 2 1s orbitals overlap, combine those orbitals to share those electrons to form a bond and to become more stable. Here's the thing we need to know about forming molecular orbitals from atomic orbitals. The number of orbitals in must equal the number of orbitals out. If we start with 2 atomic orbitals, when we make molecular hydrogen, we must end with 2 molecular orbitals. One of those orbitals will be a bonding orbital, one of them will be an antibonding orbital. This is the sigma bonding orbital. When we overlap those 2 orbitals, this is where the 2 electrons in the hydrogen-hydrogen bond live. This is the sigma bonding orbital, and we also get the sigma antibonding orbital. Notice that the antibonding orbital does not meet in the middle. There is a plane in the middle where there's no orbital contribution. That's a node. There's a node in the antibonding orbital of hydrogen. The node is where there's no orbital contribution. It's where the probability of finding an electron is 0. So this is what happens when 2 atomic orbitals overlap to form a molecular orbital. You've actually seen this before. You may have seen it in this form before, where here are the 2 atomic 1s hydrogen orbitals with their 1 electron each. They combine to form the sigma bonding orbital. That's lower in energy, more stable. That's where the bonding electrons live. And it also forms the sigma antibonding orbital. It's higher in energy. There's no electrons up there. We get these 2 molecular orbitals because we have started with 2 atomic orbitals. Number of orbitals in must equal the number of orbitals out. What's interesting with a polar bond is that the molecular orbitals of polar bonds are biased toward the electronegative atom. Now, what does that mean? It means that the sigma bonding orbital is biased towards chlorine. There's a larger orbital contribution around chlorine, and that should kind of make sense. Chlorine is electronegative. It's pulling electron density towards itself. There's more electron density around chlorine. And if there's more electron density around chlorine, then the orbital contribution on chlorine should be bigger than the orbital contribution on hydrogen. What's interesting, though, is that the sigma star antibonding orbital is also biased, but it's biased in the opposite direction. It's biased toward hydrogen. Whenever the bonding orbital is biased towards the electronegative element, the antibonding orbital is biased toward the opposite element. Okay, so what about reactions? We look at an acid-base reaction. The only way to form a bond is to pump electrons into an empty orbital. If we look at this acid-base reaction, hydroxide, oxygen is going to attack HCl, the hydrogen. We're going to use that lone pair of electrons on oxygen to form a new oxygen-hydrogen bond. The only way to form a bond is to pump electrons into an empty orbital. We've got the sigma orbital between hydrogen and chlorine biased towards chlorine. That means the sigma star antibonding orbital is biased towards hydrogen. The antibonding orbital is empty, so the only way to form a bond is to pump electrons into the empty sigma star antibonding orbital. And so let's do that. Let's move those electrons into the antibonding orbital. We're going to use those electrons to form the bond between the oxygen and the hydrogen. Okay, watch what happens as we do this reaction. Did you see it? Did you see how cool that was? The lone pair of electrons on oxygen become the new sigma bonding orbital between the oxygen and hydrogen. That lone pair orbital, the orbital that on oxygen that housed the lone pair, becomes the new sigma bonding orbital between oxygen and hydrogen. Notice it's a polar bond, so it's biased towards oxygen. The old bond, the bonding electrons between the hydrogen and chlorine, become the new lone pair on the chloride anion. And that old sigma bonding orbital becomes the new lone pair orbital on chlorine, on the chloride leaving group. Look at that. Look how cool that is. That's so cool. That's so cool. The only way to form a bond is to pump electrons into an empty orbital. So we take the OH minus lone pair of electrons, pump them into the sigma star antibonding orbital. Those electrons become the new sigma bonding, the new sigma bond, and the old sigma bond becomes the lone pair on chloride. Okay, what about an SN2 reaction? Again, the only way to form a bond is to pump electrons into an empty orbital. Let's introduce some new terms here. We have the highest energy occupied molecular orbital. Every molecule has a highest energy occupied molecular orbital. The orbital with electrons that is most energetic, highest in energy, the most reactive electrons in the system. In this case, it would be the lone pair of electrons on carbon of cyanide. Those are the highest energy electrons for this system. These electrons are going to be the best nucleophile. There's lots of electrons in the molecule, but the highest energy electrons will be the best nucleophile. The lowest energy unoccupied molecular orbital, the LUMO, is the most accessible empty orbital. It's the lowest energy empty orbital. If the only way to form a bond is to pump electrons into an empty orbital, the lowest energy empty orbital will be the most accessible and the best electrophile. That would be the sigma star antibonding orbital of the carbon-bromine bond. Again, biased because bromine is an electronegative element. So let's watch what happens. We pump those electrons into the empty orbital. As those electrons approach the sp3 hybridized carbon, that starts to build some steric clash between these electrons and the other three groups on that carbon. So the cyanide starts to push those three groups out of the way. And in fact, it'll continue doing that until it flattens it completely in the transition state. It'll have a trigonal bipyramidal transition state. So as it approaches, it starts to push those groups out of the way in this SN2 reaction, and then we get the actual reaction. Let's watch what happens. So cool. I could watch this all day long. This is so cool. What happens? Okay, the lone pair of electrons in the cyanide anion become the new sigma bonding electrons in the carbon-carbon bond. The lone pair orbital becomes the sigma, the lone pair orbital on cyanide becomes the sigma bonding orbital. The bonding electrons between carbon and bromine become the lone pair of electrons on bromide. But watch what happens at carbon. As that cyanide gets closer, it flattens out that carbon and pushes those other groups to the other side of the molecule to avoid steric clash, to avoid electron repulsion. It inverts the stereochemistry. This is why SN2 reactions invert stereochemistry. As we pump electrons into the empty orbital, look at this empty orbital. Let's go back one. This empty orbital is 180 degrees opposed to the carbon-bromine sigma bond. The sigma bond is here. That means the sigma antibonding orbital is 180 degrees opposed from the sigma bonding orbital. So it's sticking right here in that void between those three other groups. So as the nucleophile approaches, it has to push those groups out of the way to avoid electron repulsion. And then as it forms the bond, it inverts the stereochemistry. This is why SN2 reactions invert stereochemistry. It's so cool. This is so cool. I love this stuff. Next, alkene addition reactions. Again, let's introduce some new terms over here. So this molecule has lots of sigma bonds, 5 of them actually, and the 1 pi bond. So when we look at the overall MO picture for the entire molecule, it is true that sigma bonding orbitals are more stable than pi bonding orbitals. MO pictures are always symmetric about the non-bonding energy level. Non-bonding energy level is the relative energy of all of these atoms if they had never formed a bond. If they were just individual atoms floating in space, their energy would be the relative non-bonding energy level. Bonding orbitals are always more stable than the individual atoms. That's why atoms form bonds to be more stable. The sigma bonding orbitals are always the most stable, and the pi bonding orbitals are less stable than the sigma bonding orbitals. MO pictures are always symmetric about the non-bonding level. So if the sigma bonding orbitals are the most stable, the sigma star antibonding orbitals are the least stable. If the pi bonding orbitals are more energetic, if they are higher in energy than the sigma bonding orbitals, then the pi star antibonding orbital is lower in energy than the pi star or the sigma star antibonding orbitals. The MO pictures are always symmetric about the non-bonding level. So when this molecule reacts, we know that it's a nucleophile. Alkenes are nucleophiles, so we're looking at the highest occupied molecular orbital. That would be the pi bonding orbitals here. So the pi bond is the nucleophile. We already know that, but this is how the MO picture proves that to us. The LUMO, the lowest unoccupied molecular orbital, is going to again be the sigma star of the hydrogen-bromine bond. Okay, we watch what happens as the pi bond approaches, the nucleophile approaches the electrophile. And we're ready for the reaction. Here we go. You ready? Watch. When the pi bond attacks, those pi electrons and the pi bond become the new sigma bond in the sigma bonding orbital between the carbon and the hydrogen. The pi bond becomes the sigma bond between the carbon and the hydrogen. Notice also that this carbon goes from sp2 hybridized now to sp3 hybridized. And if this had been 3 different groups, then we would have formed a stereocenter. And also note that the HBr could be on the bottom here. The pi bond has a lobe on top and a lobe on bottom, so this could also happen on the bottom. And if it happened on the bottom, then we would form the enantiomer. That's why we get enantiomeric mixtures in these reactions. The HBr bond becomes the new lone pair on the bromide leaving group. That sigma bonding electrons become the new lone pair on the Br- leaving group. And the pi star orbital becomes the new empty p orbital, unhybridized p orbital of the carbocation. And look at that, look what happened. The electrons now in the Br- are now perfectly situated to overlap to pump electron density into the empty unhybridized p orbital of the carbocation to complete the reaction. It all makes sense now. It's so perfect. It's so cool. It's so cool. All right, the last one of these that I'm going to show you, and then we're going to move on to something else. Carbonyl addition reactions. Bonds are biased towards electronegative atom. Orbitals are biased towards an electronegative atom. So if we look at the pi orbital of the carbonyl, it is biased towards the oxygen because the oxygen is electronegative. If the pi orbital is biased towards oxygen, that means pi star, the antibonding orbital, is biased towards carbon. That's why carbonyls are electrophilic at carbon. Only way to form a bond is to pump electrons into an empty orbital. The empty orbital is the pi sigma, the pi star antibonding orbital. So let's do it. We'll pump electrons into that antibonding orbital. What I want you to notice here is that the OH does not approach 90 degrees from the carbonyl. Why is that? It's because the sigma star antibonding orbital is offset from 90 degrees. This angle between the carbonyl pi bond and the antibonding orbital is known as the Berge-Dunitz angle. It's about 107 degrees. It's trivia. It's really not important, but it's very interesting that these orbitals explain everything. Okay, now that the oxygen lone pair is lined up with the pi star bonding orbital, we can do the addition, the carbonyl addition. Watch what happens. The oxygen lone pair becomes the new carbon-oxygen sigma bond. We're breaking the pi bond. Those pi electrons in the pi bond become the new sp3 orbital and the new lone pair, that third lone pair on oxygen. Notice that both the carbon and the oxygen rehybridize to sp3. And again, of course, the pi star has lobes on the top and the bottom, so this O- could also attack from the bottom. And if this were to become a stereocenter, this would then be a racemic mixture of enantiomers. It's just so cool. MO's molecular orbitals explain everything. Okay, we're actually going to take a step back, actually. We're going to move back to molecules and not reactions. I'm going to look at the molecular orbitals of pi bonds. I'm going to start with ethylene, the simplest case. To make the pi bond of ethylene, we take the 2 individual atomic p orbitals with 1 electron each, and we combine them to make the pi bond. How do we do that? How do we depict that? How do we draw that that scenario? Well, actually, you probably already know how to do this. You've probably seen this in other classes before. Maybe not in this presentation, but you've probably already seen something like this. Recall from earlier that the number of orbitals in must equal the number of orbitals out. So if we start with 2 atomic p orbitals on each carbon, that means we need 2 molecular orbitals, one more stable, one less stable than the non-bonding level. Again, this is the non-bonding level. It's the relative energy of the individual carbon atoms had they not formed a bond. So 2 atomic orbitals in, 2 atomic orbitals out. They are symmetric about the non-bonding level. Just to orient you to the picture here, the squiggly line is our non-bonding level. The dots represent the carbon atoms, and this line, you could think of it as the sigma bond, but really it's just the spacer connecting the carbon atoms. It's not that important. Okay. So how do we draw the orbital picture? Again, this is part that you've probably already seen. We have the lowest energy orbital where all of the atoms overlap in phase, and the higher energy orbital where they overlap out of phase. The in-phase overlap is more stable. The out-of-phase overlap is less stable. This then gives us the bonding orbital for the lower energy orbital. That in-phase overlap leads to a bonding overlap. The out-of-phase overlap leads to a node. A node, again, is where there's 0 orbital contribution at this position. That's where the probability of finding an electron is 0. In the all-in-phase version, notice that there are 0 nodes, and we increase by 1 node for each successive molecular orbital, up to the 1 fewer than the number of atomic orbitals that we started with. So we started with 2 atomic orbitals, so our highest energy orbital should have 2 minus 1 equals 1 node. Orbitals exist, then we put electrons into them. So now that we have the molecular orbital picture, now we can consider the electrons, where they go, and what this final picture looks like. Each individual atomic orbital brought along 1 electron. That means we have 2 total electrons. Those 2 electrons will then go into the lowest energy orbital, the pi bonding orbital. And the pi antibonding orbital has no electrons in it. We know that alkenes are nucleophiles. If it was going to act as a nucleophile, we look to the highest energy occupied molecular orbital. That would be the pi bonding orbital. So when it acts as a nucleophile, it will do so using this orbital. Another interesting case of this two atom system is the carbonyl. We'll look at formaldehyde here. Again, 2 atomic orbitals are brought together, so we get 2 molecular orbitals. And orbitals, when we have an electronegative element, orbitals are biased toward the electronegative element. So the pi bonding orbital is biased towards oxygen. The antibonding orbital is biased toward carbon. Carbonyls, we know, are electrophiles. And if it's an electrophile, we're looking at the LUMO, the lowest unoccupied molecular orbital. That would be this one. And there is a greater orbital contribution from carbon than there is from oxygen because the biased towards the electronegative element. Because there's a greater contribution on carbon, that's why we know that carbonyls are electrophilic towards carbon. Yes, we could have proved that through resonance, but resonance is just a human construct. The MO picture is what the orbitals actually look like. Next, we'll look at butadiene. It's a 4-atom system with 2 pi bonds. Number of atomic orbitals in must equal the number of molecular orbitals out. So each individual carbon atom is going to bring along a p orbital and an electron. So that's 4 atomic orbitals. So that means we need 4 molecular orbitals. How do we do that? How do we draw that picture? Again, they must be arranged symmetrically about the non-bonding level. That means we'll have 2 more stable orbitals, 2 less stable orbitals. That means we'll have 2 bonding orbitals and 2 antibonding orbitals. But how do we draw the MOs for this picture? Well, the lowest and the highest energy orbitals are always the easiest to draw. The lowest energy orbital always has all in-phase overlap, and the highest energy orbital always has all out-of-phase overlap. Notice that we have 3 nodes in here. We started with 4 atomic orbitals. 4 minus 1 makes 3 nodes in the highest energy orbital. And down in our lowest energy orbital, we started with 0, all in-phase overlap. And the number of nodes is going to increase by 1 with each successive MO. So this one had 0 nodes, so we'll need 1 node, 2 node, and then we get to 3 nodes. But how do we do that? How do we draw those nodes? Where do we put those nodes, and what do the orbitals look like? Well, each molecular orbital must be symmetric about the center of the molecule. So when we have 1 node, that 1 node will go right in the center of the molecule. These 2 orbitals will be in phase, and then we'll have an out of phase for the node, and then we'll have 1 more in phase overlap. For 2 nodes, again, we'll put them symmetrically about the center of the molecule. So we'll start with an out of phase overlap, and then an in phase overlap, and a final out of phase overlap. And then we get to the third, the 3 nodes in the 4th molecular orbital. Again, symmetrically oriented, and they're all out of phase overlaps. One other interesting thing about these pictures, if we look down here, if we look between carbons 1 and 2, that's an in-phase bonding overlap. If we look between carbon 2 and 3, that's a bonding overlap. If we look between carbon 3 and 4, that's a bonding overlap. So this has 3 bonding overlaps. If we look at MO number 2, between carbon 1 and 2, we have an in-phase bonding overlap. Between carbon 2 and 3, we have an out-of-phase anti-bonding overlap. And between carbon 3 and 4, we have an in-phase bonding overlap. So we have plus 2 bonding overlaps and a minus 1 anti-bonding overlap. So if we look at the net bonding picture of MO number 2, we have plus 2 bonding overlaps, minus 1 anti-bonding overlap. We have a net plus 1 bonding overlap of MO number 2. Down here, we had a plus 3, minus 0, plus 3 bonding overlap for MO number 1. So plus 3, net plus 3 bonds, net plus 1 bonding situation. If you look at MO number 3, we have a out-of-phase antibonding overlap, in-phase bonding overlap, out-of-phase antibonding overlap. So we have plus 1 bonding, minus 2 antibonding. So this is a net minus 1 bonding situation, a net antibonding situation. And here we had a net minus 3. So we started with a net plus 3 bonding situation to a net plus 1 to a net minus 1 to a net minus 3 bonding situation as we went from as we went up in each orbital. The net plus 3 bonding situation is the most stable. It's the most number of bonding interactions. Then we had plus 1, that was a little bit less stable, a little bit higher in energy. Then we had minus 1, that's net antibonding, so it's above the non-bonding levels, our first antibonding orbital. And then we have net minus 3, that's the least stable situation. Orbitals exist, then we can put electrons into them. So now that we have the orbital picture, we can look at the electrons. Each carbon atom brought along 1 electron. So there are 4 electrons in this orbital picture. Now we can add them to those orbitals. So they'll go in the bottom 2, the 2 bonding orbitals, and the 2 antibonding orbitals will remain empty. How about 3 conjugated carbon atoms? If we have 3 conjugated carbon atoms, for them to be conjugated, this carbon needs to be sp2 hybridized so that it can have a p orbital, which means it's going to have a charge. Which charge will it have? Actually, doesn't really matter whether it has a positive charge or a negative charge, because orbitals exist, and then we can put electrons into them. So all we need to really know is that this is going to be sp2 hybridized with the p orbital, and we can worry about the charge and the electrons in a little bit. What that does mean is that each of these carbons has a p orbital, which means we have 3 atomic orbitals, which means we're going to get 3 molecular orbitals. But how do we arrange 3 molecular orbitals to be symmetric about the non-bonding level? We've got the non-bonding level here. Where do we put those 3 orbitals so that they're symmetric about the non-bonding level? Well, we can put 1 below, we can put 1 above. What about the 3rd molecular orbital? It will go at the non-bonding level. It will be neither stabilized nor destabilized relative to the individual carbon atoms had they not been bonded. So this is how we arrange those 3 orbitals when we have an odd number of molecular. How do we draw the molecular orbital picture then? Again, the lowest and highest energy are the easiest to draw. The lowest is all going to be in phase 0 nodes. The highest energy is going to be all out of phase 3 minus 1 equals 2 nodes. What about this center, this middle molecular orbital, MO number 2? We went from 0 nodes to 2 nodes, so this is going to have 1 node. How do I put 1 node in this molecular orbital? Again, it's got to be symmetric about the center of the molecule. So where does the node, how do I get 1 node in MO number 2? The node goes at the carbon atom. That's cool. The node goes at the carbon atom. There is 0, so what this means is that carbon number 2 has 0 orbital contribution to this molecular orbital. There's no probability of finding an electron at carbon number 2. That's where we get our 1 node and still be centrally symmetric about the center of the molecule. That atom has no contribution to the molecular orbital. We've got our bonding orbital, our antibonding orbital, and we have this one in the middle. If we look at the bonding picture for this one, here we have an in-phase bonding overlap, here we have an in-phase bonding overlap. So we have 2 bonding overlaps, a net plus 2 bonding over here. In the top one, we have antibonding and antibonding, so we have a net minus 2 orbital picture here. What about in this middle one? Between carbons 1 and 2, there's really nothing. There's no orbital on carbon number 2, so it's neither bonding nor antibonding. Between carbons 2 and 3, again, there's no orbital here, so there's really nothing. There's no bonding or antibonding. Carbon 1 and carbon 3 are too far away. Those orbitals can't overlap. So what kind of bonding picture do we have here? We don't have a bonding or an antibonding overlap here. We don't have a bonding or antibonding overlap here. So the net bonding contribution for this orbital is 0. The orbital here at the non-bonding level has no bonding or antibonding contributions. It is a not bonded orbital. It's so cool how this all plays itself out. We went from a +2 to a 0 to a -2 bonding contribution for each of these molecular orbitals. Now, the fact that we have a node at a carbon, really not a big deal, really not all that uncommon. Don't worry too much about it. Orbitals exist, then we put electrons into them. But how many electrons do we have? We didn't really decide what was going on with this 3rd carbon, because it depends on the charge, how many electrons that we have. If it's a cation, then there's no electrons from this carbon, and we just have the 2 electrons from the pi bond. So we only have 2 electrons, and so they go in the lowest molecular orbital. Now, this cation is an electrophile. We know because it has a positive charge. And if it's an electrophile, that means we look to the LUMO. That would be this lowest unoccupied molecular orbital would be here. And if we look at the LUMO, there's no orbital contribution on this central carbon. So we can be electrophilic at carbon 1, we can be electrophilic at carbon 3, but we're not electrophilic at carbon 2 because there's no orbital contribution on carbon 2. That's predicted by resonance. We could put the positive charge here, we could put the positive charge here, but we never get the positive charge on carbon number 2. But that's borne out in the molecular orbital picture. It's just It's just so cool. If we look at the case where now this is an anion, now this carbon has 2 electrons, a lone pair, so that means there's 4 total electrons in this orbital picture. So we'll put 2 here, 2 here. This is an anion, so it is a nucleophile, so look to the highest occupied molecular orbital, that would be MO number 2. Again, there's no orbital contribution at the central carbon, so we can be nucleophilic at this carbon, we can be nucleophilic at this carbon, but we can never be nucleophilic at this carbon. Again, that's played out through resonance. We can put the negative charge on this carbon or this carbon, but we never get the negative charge on the central carbon. But interesting, between the cation and the cation was an electrophile, so we looked at the LUMO. The anion was a nucleophile, so we looked at the HOMO, and that's the same orbital in both cases. Where the same orbital in both cases proves that one is a nucleophile, one is an electrophile, and proves that it's not the central carbon, but it's the 2 outer carbons that are the reactive carbons. Now, the 3-carbon system is also very interesting, or the 3-atom system, I should say. The 3-atom system is also very interesting in the enolate. Enolate has the electronegative oxygen. Orbitals are biased towards electronegative elements. So what does the MO picture of the enolate look like? Well, it looks like this. Enolates are negatively charged. They are nucleophiles. We see that the lowest energy orbital is biased towards oxygen. The next orbital is biased towards carbon. When we look at the highest occupied molecular orbital, because the enolate's a nucleophile, that would be MO number 2 here. And we see that the orbital contribution from carbon is greater in MO number 2 because of the biased orbitals with the electronegative oxygen. What does that mean? If the orbital contribution on carbon is greater than it is on oxygen in the highest occupied molecular orbital, and if this is the orbital that the enolate uses to be a nucleophile, and there's greater contribution on carbon, it proves that enolates are nucleophilic at carbon. They are preferentially nucleophilic at carbon because the greater orbital contribution comes from carbon in the highest occupied molecular orbital. It's just so cool. It's just so cool. Okay, let's circle back to some reactions and see how all this plays out. We'll look at 1,2 versus 1,4 addition of conjugated dienes. This molecule is a butadiene, so it's a 4-electron, 4-atom system. We already saw the MO for that. This is acting as a nucleophile, so we look at the highest energy occupied molecular orbital, that'll be MO number 2. And what we see is it really kind of acts like 2 isolated pi bonds. Either of these pi bonds could attack HBr in the first step to form the carbocation. We'll do that to follow Markovnikov's rule, so to form a carbocation that's the most stable. Then we get the resonance stabilized intermediate, and look at that. This intermediate is a 3-atom 2-electron system. It's the allylic cation system. 3 atoms, so 3 MOs. We've seen this MO picture before too. This MO is, or this molecule is an electrophile. So we look at the lowest unoccupied molecular orbital, that'll be MO number 2. And when Br- attacks, it's going to attack the LUMO, the lowest unoccupied molecular orbital, that would be this one. So when it attacks, it has orbital contribution on carbon number 2 or carbon number 4, but never at carbon number 3. So when Br- attacks, it can either attack carbon number 2 or carbon number 4, but it can't attack carbon number 3. There's no orbital contribution at carbon number 3. So when Br- attacks, we either get the 1,2 addition or the 1,4 addition product, but never the 1,3 addition product, because the MO picture has no orbital contribution at carbon number 3. It's just, I just can't, it's just so cool. And then just to kind of close the loop, we end up with just a regular pi bond, and so we end up with a 2-orbital, 2-electron system that we can then do other chemistry with if we really want to. Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.